work of late Professor Roddam Narasimha. I don't know how many of you have heard of his name. He was a very important scientist, engineer in India. He was basically director of the National Aeronautical Laboratories in Bangalore. Later on, Center for Atmospheric Sciences in Indian Institute of Science. He was decorated with Padmashree in, I think, 2012 or 13, Fellow of Royal Society and all that. So, Roddam Narasimha, if this issue is to be discussed, then I will give some background. He's from Bangalore, of course. Comes from an educated Orthodox family. His father was actually a professor of physics in Bangalore University, Central College. He also wrote extensively in Kannada. In fact, when I was a student in Bangalore in 50s and 60s, we read some of his popular astronomical works and all that. Then Narasimha did his BSc, and then there was a 2-year diploma in engineering which Indian Institute of Science offered. It was not having undergraduate courses till about 2000, perhaps almost till then. Then he did postgraduate work there and started research on a project when the director of Indian Institute of Science, a fairly famous scientist called Satish Dhawan, he was head of Indian Space Research Organization. Satish Dhawan was also an alumnus of California Institute of Technology, Pasadena. So he asked Narasimha to go and do PhD in fluid mechanics and turbulence and all that in Caltech. And so after that he returned to India and was associated with Indian Institute of Science or Aeronautical Laboratory, etc. So he has done major work in the area of chaos, fluid flow systems, Navier-Stokes equations, and more about cloud formation and things like that, and monsoon, all these things, different approaches. So in the last few years of his life, he was associated with another institution called the Jawaharlal Nehru Center for Advanced Scientific Research, set up by Professor C.N.R. Rao. He and C.N.R. Rao were classmates actually from school onwards. Around 2000, I mean, of course, there are various interviews of Narasimha, which I sent it to him. You can all read that. He got interested in the question of, I mean, he says in the various interviews that when he went to US, he was confronted with a situation that he was extremely well prepared for the course of study there, which meant that we were fairly well aware of what's going on internationally, even to the extent of being able to participate in the frontiers. But then the ease and the system through which they navigated and worked is not something that we are or we have been unable to establish here. So he was wondering, so what happened? I mean, is it a new problem, old problem? And so he got interested in wanting to find out whether India had any important contributions in science and engineering through its history. Scattered material was available in Caltech also, but there were professors who knew more about India. And since he was well trained in Sanskrit, etc., through family and in his school education and college education, he could sort of look up books, and so he has pondered over this question, say, from about 1965 onwards, looking at it along with his work. But he started writing about it around 2000, and he has written about 8 to 10 articles and has given a couple of interviews on this. Unlike many others, Professor Narasimha's work focuses on two questions. One is, there is a question which was posed by a British scientist, historian of science. Joseph Needham was a biochemist. He was also a Communist Party card-holding member. So in 50s, he got, I think towards the end of Second World War, he got interested in because he had a graduate student, he was in Cambridge, students from China and all that. So he got interested in the scientific heritage of India, and UNESCO sent him to China for a couple of years and all that. So he ended up initiating a massive project on the development of science and technology in China. And perhaps most of you are aware of about 12 to 14 volumes called Science and Civilization in China have been published by the Cambridge University Press between 1965 to up to 2000 or 2005, covering all subjects. The first two volumes are a general history of philosophy of science as was practiced in China and technology. Then I think next is on physics, then mathematics and astronomy, then physics, then engineering, then chemistry, then biology, even language, logic and all that, medicine. So all that has been covered, earth sciences. So from about 1970s, Professor Needham started writing and giving talks on what he had understood by his 20-25 years of acquaintance with China. And so two questions he sort of posed. One is that from his study, it appeared to him for about 1400 years, from the 2nd century of the Common Era to about 1600, both China and India had outperformed the rest of the world in science and technology. So, as Professor Narasimha says, this is the first time he saw a major Western scientist sort of acknowledging this, that for these 1400 years we were China and India were the leaders in science and technology. Second question was, or this was an observation, but he says that what happened in Europe from about 16th to 18th century and later, why that did not sort of take off. So why was it that it was in Europe, in Paris or Pisa, all this happened, and not in Patna or Peking, Beijing? So this is called the Needham question, that why modern scientific revolution did not take place in the countries which were most advanced in science and technology in 16th century, China and India, and why it took place in the West. Of course, from then onwards, there's an enormous literature. People have tried to answer it in various ways, both from within the science and technology domain, giving internal causes, and from the social and cultural domain, giving external causes for this. So what Professor Narasimha's special sort of approach to this was, one is to, of course, make Indians aware of this fact, that it is now well established that we had whether we were leaders or not, we had a very substantial contribution to science and technology in this period. Much of this period after the 4th century Common Era, it's called the dark period in Europe till about 13th, 14th century. So in this dark period, it was the bright period here. So to make our people better aware of this, and so he looked up basically about what was Indians' view about science, scientific knowledge, technology, and how did they do whatever they did, say, in astronomy, in mathematics. Mathematics especially, till about 16th century, after the Greek period of about 3rd century Common Era, till 16th century, India was, most mathematicians, historians who have studied this subject deeply, will acknowledge that most major contributions did come from India. And he also looked up more experimental sciences and things like that. So he had a view that there is something different in the way Indians approach science, in the way they understand science, the way they formulate questions, the way they answer them. And this he immediately pointed out by first looking at the books of science themselves. So there is this famous book called Aryabhatiya, which was written by Aryabhata in 499. It is an exposition of mathematics and mathematical astronomy. So it has one initial part, it's called the Gitika Pada, consisting of about 10 to 12 verses, which give various parameters, numbers for various things, physical parameters, astronomical parameters, some conventions of how numbers are formulated in the book, because this is a book in verses. So in all about 108 verses are there in a meter called Arya. And so these numbers all had to be stated in the middle of the verse. So the first number that comes is what is called the period of a Mahayuga, which is 43,20,000 years, in which how much do various celestial objects move. So this 43,20,000 years, Aryabhata denoted it by just two syllables called Q-gr. Q-gr represents 43,20,000. So he had to give this coding, how to code numbers by linguistic phrases, or just so this was one of the innovations. There are many other methods, but so this gives all these parameters in 12 verses. Then there is something called the Ganita Pada, mathematics part, which is 32 verses. Then there is something called the Kala Kriya Pada, determination of time, that has the basic statements about planetary model, Earth and the Moon and the 5 other planets that were considered in ancient times: Mercury, Venus, Mars, Jupiter, Saturn. And their other orbital points like apogees or nodes or things like that. So discussion of them. Last part is called Golapada, which what we today call as spherical astronomy. How do we measure the motion of these? By using various techniques, mostly a gnomon and its shadow or other astronomical instruments, and how to mathematically compute all that. So he introduced what is called the sine function in trigonometry for the first time, one of the oldest books to introduce that function and use its properties in formulating all this. So what Narasimha saw was, he tried to compare this with another great classical book of astronomy in its history. Is called the book Mathematical Syntaxis by the Greek astronomer called Ptolemy. This was written in 150 of the Common Era. Aryabhata's book can be written in 3 pages in normal typeset. This takes about 500 to 600 pages of writing. It is called Almagest otherwise. The Arabs called it Al-Majesty, the greatest book. So the way Almagest deals with astronomy and the way Aryabhata has dealt with astronomy, mostly they are talking of similar things, trying to tell you. Of course, Aryabhata would need a complete exposition by a teacher to understand, because it's in a very compressed form. So a commentary is needed. So the oldest available commentary to us is a commentary called Aryabhatiya Bhashya by one Bhaskara, not the more well-known Bhaskaracharya of the 11th century Maharashtra, Karnataka region. This Bhaskara lived in Gujarat. So he wrote the first Bhashya, no available Bhashya. Then there are several commentaries, at least about half a dozen commentaries have been published. So the first article of Narasimha was on a sine table. What is a sine table? It's like Clark's tables, only Aryabhata gave the table in one verse with his coding. And what he gave was the sine values for 24 angles, 3 degrees 45 minutes. Divide 90 by 24, Each bit is 3 degrees 45 minutes. So for these 24 bits, he gave the sine value. So 3 degrees 45 minutes, then 7 degrees 30 minutes, like that it goes. So first paper of Roddam Narasimha was on the sine table of Aryabhatta. It's called Maki, Phaki, Phaki, etc. It goes like that. He actually is giving the difference of signs in that verse, 24 sign differences he gives it. Then, so like that, he started pointing out one after the other in his various articles. So then he arrived at a position called what he calls as computational positivism is something that is characteristic of Indian approach to science. So what does he mean by this? That if you pick up any book of mathematics or astronomy, or even of architecture or chemistry, or even yoga, what these books state are not laws or theorems or general statements. They may have some of them, but there will be only few of them in the book. The books will tell you what the books themselves call as vidhi, prakriya. That is the way to do something, the procedure for doing something. So the books deal with giving systematic procedures for accomplishing, calculating, or doing various things. So the Yoga Shastra may tell you how to ultimately arrive at Chittavritti, Nirodha, Samadhi, or whatever. So the astronomy books will tell you how to calculate the positions of planets and how to use that knowledge to find out the time on the surface of the earth, to find out our location, latitude, longitude on the surface of the earth, to find out the direction in the location of the earth. So all these three things are to be determined by knowing the position of planets, sun, moon, and the five. Mostly sun, moon, actually, for this purpose. And so the what is called the Goladhyaya of Aryabhatiya is mostly on this. And you take any book of Indian astronomy, older book, say Bhaskaracharya in 1150 wrote a book called Siddhanta Shiromani. It has about, I think, 500 verses or something like that in its first half. It's two halves. So of those 500 verses, about 250 are on this particular thing. How to determine from the shadow or from the instrument the coordinates of various celestial objects, and how to also using that determine the directions here, position here, time here. So from the shadow, how to determine the time during the day, all these things. So this will be the main part of the book. So the first two chapters of the book will tell the how to calculate the position of the planets as seen in the sky, and then the second half will tell you how to observe them and check whether that is correct and how to use this information. So these are in this set of procedures. They have a very simple name today in modern parlance. It's called algorithm. Algorithm initially, of course, meant how to do arithmetical calculation. The word algorithm comes from the name of a Central Asian mathematician, astronomer called Al-Khwarizmi. He's from Uzbekistan, and he then shifted to Baghdad. And he wrote in around 820 a book called Hisab al-Hindi. Hisab means Hisab Rakna, Ganit Karna, calculation as per the Indian way. And what he discussed was what we today call all the arithmetical algorithms that Indians did, using what is called the decimal place value system. And then something about trigonometry, something about equations and all that, all this. So this book, when it was translated in Europe, so they called it Al-Dixit Algorithmi. This is what he said. And this method of doing thing became the algorithmic way of doing, because till then, two things, they were not using the decimal place value. They use what is today known as the Roman numerals. As you know, Roman numerals, if you just have any number, MD, X, IIR, whatever, it's very difficult to do any calculation with that. So all the systematic methods of calculations, which are very important not just for arithmetic sake, but for all ordinary commercial dealings and ordinary living. So this word became, algorithm became therefore the name for any systematic procedure for doing something, calculating. So the books in India deal with procedures and not what is usually called in logic propositions. Proposition is a general statement. Then the question is true or false or things like that. When you say you are talking of a procedure, you have to see whether it's effective, non-effective, optimal, whether it takes you to the result, whether it is like that. So the way you judge a procedure is different from the way you judge a proposition. So this thing was one thing characteristic of Indian texts, which Professor Narasimha noticed. So they indulged in computation in everything. Computation in the most generalized sense, not merely numerical computation, symbolic computation, practical procedures. Only it was not being done by the computer, but done by humans. So this was the first thing. So then what is positivism about that? So now when you have a procedure, or when you compute, when you calculate, in astronomy when you calculate the procedure, crucial thing is what you calculate and what you observe should tally. There should be a consonance. So these astronomers had a word called Drig Ganita Aikya. Drig is what you see, Ganita is what you compute, they should coincide. So he used this as the astronomical, and in mathematics, you have a procedure to solve an equation. The procedure should actually lead to a solution of the equation. So this, he said, is the crucial thing in computation. Most important thing is it should lead you to the result. So in any procedure that the texts say that you do all this, this is what is the end result expected, you should get that result. So if it's a chemistry, sort of a preparation of a arca or whatever, so the book says do this, take this, take this. Or in medicine, it says you do this way of first diagnosis, then this treatment. Does that do that? So everywhere the efficacy, the validity of the procedure is the main thing. And the general attitude seemed to be that any procedure which leads you to the desired result is good enough. So whether it is based upon a very thorough fundamental understanding of the universe or of the system or of the, that was not of a major concern. So this is similar to something that was discussed in Europe in early 20th century in a group of philosophers called logical positivists. I don't know how many of you have heard. So Rudolf Carnap was one. I think there were about half a dozen. I think they were called Vienna Circle or something like that. And so they said that science should not be dealing with what they called, quote unquote, metaphysical. Unnecessary metaphysical baggage should not be there in science. It should deal only with observable, verifiable things. And so he took that word positivism, and I think it goes back in social sciences to Augustus Comte, I think the founder of sociology. I think he's the oldest positivist or whatever. So he coined this word computational positivism to explain this methodology that is found in Indian sciences and Indian scientific practice. And now to contrast this with Europe, what we had. So what does Ptolemy's book have? what does Euclid's book have? So they start with a detailed set of assumptions. Of course, I am just using the general word assumption or postulate, but there is a very technical term called axiom. Axiom may mean something very technical in Euclid's book. It means something that is self-evident and true, whose truth is self-evident. So Euclid starts with 10 axioms, I think, 5 which are called general axioms for all mathematics. If you add equals to equals, you get equals and things like that. And then he has 5 specific to geometry that he is doing. If you have 2 points, there is a single straight line that passes through them, things like that. And it will have some definitions. And so it starts with the axioms, and then various conclusions are drawn using standard deductive logic, basically old Aristotelian kind of logic. So even in what is called astronomy, they had a similar way of going about. So first a model will be described in full. Before the model, the philosophical precondition. So if it comes to astronomy, the idea from the time of Plato was that we have to discuss these motions of celestial objects by means of uniform motion along a circle. So this is what is there in Plato's Timaeus, or one of those famous philosophical books, that the way to discuss. And why it is so? Because these are celestial objects. Professor Narasimha doesn't go into this kind of, for your information, the way astronomy, and in fact it had a great impact on all other sciences, physical sciences, was formulated by both Aristotle and Plato. Of course, they had different philosophies. It had basically this connotation. Below the lunar sphere, whatever we have, there is nothing much very regular about what happens here. The bodies are, the way they behave, the way they move, they are called corruptible bodies. They are made up of the 4 elements: earth, water, fire and air. Above the lunar sphere, all the bodies are made up of an ideal material called ether. They are all perfectly spherical, and they perform highly regular, mathematically regular motion. So, and all this is controlled by something called a demiurge, who sets all this in motion. The sphere of stars is there, afterwards the sphere of Saturn, then the sphere of Jupiter, then the sphere of Mars, then the sphere of Mercury or Venus or Sun. The order in which you place depends on person to person. And then the sphere of the moon, then Earth. And those bodies all move very regularly. And that is what is genuinely the subject that a philosopher should look for. You get beautiful laws which are eternal, unchanging, accessible to mathematics, accessible to computation. And this should be what the philosopher should look for. Philosophy then meant natural philosophy, which is later on called physics, and astronomy. So this is how the great focus on astronomy in Greek science was. And so the focus below the lunar sphere, there was very little of it in terms of this kind of uniform laws of motion or uniform principles of motion, because the bodies are not ideal. Aristotle's mechanics was very simple. The 4 elements: earth, water, air, fire. Fire and air move up, that is their natural tendency. Water and earth move down, that is their natural tendency. For them to do anything else, some force has to be applied. So this was all of Aristotle's physics basically. And then there is this astronomy. Aristotle had a very complicated set of circles and all that, which was not very effective. By the time Aristotle is 3rd century, he was the teacher of Alexander. So he is around 320. And from him to the time of Ptolemy, through various people, Apollonius, first who devised this epicycle, Hipparchus, who worked out the lunar motion and all that. But there was a great input of observational data from a civilization which hardly we talk about in the older histories of science. Any of you know what that civilization is? Mesopotamian civilization. They had a record of observation from about 1500, some in mathematics from even 2000 before the Common Era. And this great set of observations, which are now being published for the last 150 years, once the Europeans went to West Asia and started in the area, Iraq basically, in the what is called the Doab there. That's the Mesopotamia, between the two rivers, Euphrates and Tigris. So in those great cities, in those temples of those times, huge amount of these cuneiform tablets are there, which were all written on this thing, clay tablets, written and baked. So they are sort of unerasable kind of a thing. So from about 1900 onwards, this is being published, and it's a huge amount of, there are about a dozen universities in America and a dozen places in Europe which specialize in study of this. So they are in Akkadian, then later on, what is the other language of Mesopotamia. So this is this was the input, all this. So what was the period of moon? They knew up to the 6 decimal places. Moon as seen from the earth in the movement of stars. They knew, so for moon once to go from the star that you see with the moon today, again back to that star, it's about 27 days. That's why we have this 27 nakshatra system. It's about 27.53 something, 067. So up to 5 decimal places they knew that. And that was the input to the mathematical sort of framework that the Greeks coined. First Hipparchus, Apollonius, then Hipparchus, then Ptolemy. So they had this model. Then from that, of course, they didn't have our arithmetic. So calculations were fairly difficult. The Babylonians had a place value system with the base 60. So calculation is difficult even there. They had one symbol for 10 and one symbol for 1 to 9. So it was not a single, not 9 digits, which are just 9 symbols. So if you write 53, 5 symbols for 10 and 3 symbols for 1 had to be put. Of course, but they had a place value system. They could do beautiful calculations of square root of 2 to 5 decimal places and things like that. This is in 1800 BC. So all that system they adopted. But the Greeks were specifically geometry oriented. So they made this geometrical model, but calculations had to be made. Now in geometrical model, to make calculations, you have to do fairly complicated way of doing it. And so they would only produce tables. For everything, tables were given. So Ptolemy's book is full of tables. He has a table of chords in a circle. Then he has tables for every phenomenon. So this was the way of doing science. So there is a model, then there are conclusions drawn from it, then calculations are made from that. And this model also has parameters. So you make observations, and if the observations don't tally, you either change the parameters, you recheck the parameters. So the various parameters, say the Earth's axis is inclined to the plane on which the Earth moves. It's not perpendicular to that plane. It is inclined. But that inclination, which is around 23.5 degrees or something, it's variable. It's between 24 and I think 22.5 or something like that. Over a period of 30,000 or 50,000 years, it changes. So at each time, you should know what it is. So like that, you have what is called the period for Earth to go around the sun, or as we see from the Earth, if the sun is in one star today, for the sun to come back to the same star, that is called the solar sidereal year. Roughly 365 days, but actually it's 365.256, etc., etc. So like this, various parameters have to be corrected. Models have to be. So the model that the Greeks discovered was based upon a philosophical principle, goes back to Plato, that everything moves on ideal, uniformly on circle. Only they appear to go faster and slower because the center of the circle is not the earth. So like that, and Ptolemy included another complicated thing called equant and things like that. And this is how astronomy developed in Greece. And for the almost next 1200 years, there was very little change in astronomy. It went to the Arabs. Indian astronomy also went to the Arabs. So the Arabs took Indian methods of calculation, Indian algebra, but they took the Greek model of Ptolemy and they developed it further using Indian methods of calculations, Indian trigonometry, Indian algebra. So this is what reached back to Europe in 12th, 13th, 14th century. And again, sort of, there was discussion on whether Ptolemy's system is correct or not. And so all this discussion, Arabs also had, the Arab meaning West Asia also had this discussion. So this method of making a full-fledged model with axioms and then parameters, calculation, then checking, and then progressing in science. So Professor Narasimha tries to contrast these two systems, and both the systems emphasize ultimately that your calculation should coincide with what is seen. Both the systems say that you should make calculations. So at these two there is no. So where does it differ? Indians seem to put all the effort on the procedures of calculations. The model is described in a very brief manner. And as and when some new calculation is to be made, a new hypothesis are added, new principle is added, new calculations are made. There is no complete, though in the beginning there is something stated as the general thing, all things go around the earth and few generalities. Actually, as you go through the book, you will see specific things are made for specific things and calculations are described. And there were different schools of calculation. So in Indian astronomy, they are called various pakshas. So there was in Varahamihira in 550. Aryabhatta is not the first astronomer of India. Varahamihira in 550 wrote a book called Pancha Siddhantika, 5 Siddhantas. And these are older Siddhantas, older than Aryabhatta. So Surya Siddhanta, Vasishtha Siddhanta, Paitamaha Siddhanta, Romaka Siddhanta, and Paulisha Siddhanta. 5 Siddhantas he wrote. So all of them he is explaining how calculations are made in them. So there were multiple frameworks. Of course, the Surya Siddhanta became famous. What is called the Brahma Siddhanta or Paitamaha Siddhanta became famous. The Aryabhatta's version became famous. They carried on for a long time. But changes were made, improvements were made. But the Siddhanta was not the most important thing. The algorithms and efficacy of the algorithms was the important thing. So Professor Narasimha tried to view it this way. So this is first half of the story. How? So anyway, the Greek science, since it didn't concentrate on most of modern physics or chemistry and biology in the way sciences developed in India, because we didn't have the principle of the ideal motion only in the skies or whatever. So there were various sciences. In fact, India had 3 famous major sciences. One was the science of language. Language is a physical phenomenon and Indians tried to treat it systematically. Second was the science of astronomy and mathematics. Mathematics arose in the context of astronomy. It also arises in language also, in prosody, in music, etc. And then there is the science of Ayurveda or art of Ayurveda, technology. That is also a very major science because it combines pharmacology, chemistry, material science, understanding of the human body. So all these are together. But the purpose is very particular. Purpose is how to understand a situation where somebody feels unwell. His swasthya has been disturbed. Aswasth ho gaya hai. So how to understand that and how to restore his health. So and how to preserve somebody who is healthy to be, meaning how to see that one continue. So they had kept that as the focus and around that the entire framework of Ayurveda. But A huge amount of 700 herbs are discussed, 500 animal products are discussed, and they are categorized in terms of various qualities and properties. And the human body's disorganization is characterized, both mental, physical, are characterized by various sort of frameworks, and then sort of methodologies are developed. So it's an enormous, so the oldest or the greatest books of Charaka or Sushruta, they run to thousands of verses and their commentaries. And then of course there's a very famous book called Ashtanga Hridaya, which in 6th century summarizes the essence of both what is said in Charaka and Sushruta, which became the major text for practice in most of India for a very long time. Anyway, so this science didn't develop in a very systematic way. Of course, we always talk of Hippocrates and then Galen and all that. So, but the way Indian sciences developed in this was at a very huge pace, and the kind of pharmacopoeia they developed, and the kind of methodology they developed, the kind of framework that they developed was a very detailed one. So, the sciences in India, but Professor Narasimha doesn't look into this. But he is able to understand that we were very, very systematic observers and calculators, according to him. Or we build a system of algorithms after observation, which is after all a theoretical matter. Algorithm is not a pure record of a single observation. It's a procedure to calculate something. So it is based upon, say, the square root algorithm of Aryabhatiya depends on the decimal place value system. And then you have to go and depends on a certain relation between a plus b whole squared is a squared plus 2ab plus b squared and things. So that's how things work. But the focus was not on those principles, focus was on algorithms. So multiple theories were allowed, multiple formulations were allowed, they were talked about. So therefore, there is no emphasis on the theory, the true picture according to which heavens move, as the most Greek thinkers thought, or Copernicus thought. So that true philosophy by which humans use language. So there is no discussion on that kind of a. So how to understand the language? The other questions are discussed, but they are in the light of satisfying better grip on analyzing language, understanding language, producing correct words. So the focus is here. And similarly, what constitutes life is not the main question. Life is taken, that it's there. So the issue is how health gets disturbed and what is the way in which we can make this longevity reasonable, as much reasonably long as possible, not make eternal longevity. So like this. So Professor Narasimha understood all this, but then he tries to understand why we miss the bus. I think I will finish in about 5-10 minutes, then we will have discussion. So this is the more crucial question he addresses, that we seem to have missed the bus in 16th century. So why did we do that? So his view is two things. One is the Western European science came back to look at the world once again. They were only looking at the skies in their abstract sciences or exact sciences. But you can have an exact science of matter and motion and materials and all that in the natural domain, which was called the corruptible domain in the Greek philosophy. So this started in 13, 14, 15, 16th century, even in Europe. Understanding of motion beyond what Aristotle had discussed. That Aristotle's idea was that body moves, keeps moving only when as long as a force is acting on it. So it's something like force is proportional to velocity, not force is proportional to change in velocity. That. So this was there only 13, 14, 15th century, this one started getting discussed. So because of various things, warfare technology in a big way, so projectiles, firing of guns and motion of them and various other things. So so this new science had to have more firmer position about what we observe as being the major source of scientific activity. There was hardly, in fact, Plato even said that you don't need to look at the skies as long as you know how they move. It's only for ordinary people that they should go on observing this. So that's the kind of philosophy they had. But from that they moved on to the idea that you should also go out and conquer the world, control. All these things came together in a more concentrated focus on how Chinese, others, the West Asia, others have progressed in various material sciences and what we can learn from them. So this arithmetic, this algebra, this chemistry, this medicine, this physics, from various areas, they flowed them back to Europe. Of course, they regained the older Greek texts also. And they said the Greek philosophy is the philosophy, but we know the Greeks had only the Mesopotamian data. Now we have the data from all over the world and the principles they have used. So we will now create a new science. And that's how they set about doing it. But the focus was that these axioms are not self-evident truths. They are generalizations from observation. And this is the kind of thing that a person called Lord Francis Bacon wrote in his various books. And so this is made a very great deal of that. Bacon is discovered as the modern philosopher of science, and this process that you have to observe and infer principles from that, and then they become your axioms or basis of the model. And Bacon wrote a new logic. Aristotelian logic was just simple thing, all men are mortal, Socrates is a man, therefore Socrates is mortal. So this kind of syllogisms and simple deductive arguments formed the basis of Aristotelian logic. Bacon tried to show or claimed that he is giving you an engine by which you do all observations and deduct some principles. So he called Novum Organum was his famous book that Aristotle had written a book called Organon. So this is a thing that the world is important, and that is from where you get your principles. And these great inventions have happened. Bacon said that he referred to 3 great inventions which were cause of the progress of Europe in the sort of in conquering areas. In Bacon is around 1580 to 1650. Conquest of Europe of the rest of the world starts around 1430, 1440 and things like that. First the reconquest of Spain and then conquest of the rest of the world. So this philosophy was one that this knowledge is power. And this is the knowledge that God has given us, that we have to know the world and control the world. And that's the Christian understanding of that God has bequeathed a certain dominion of earth to humans. So all these combined. So he gives what we today call as the principle of induction. And to do this induction, certain, not merely looking 10 instances, you cannot arrive at a principle and say that you have discovered a new principle. You have to put it into check in various ways, how this is to be done. So how general results are obtained from lot of particular observations. Now only Bacon's error was he claimed he had produced a sure enough method. So if you do it this way, this way, this way, you will sure enough, he is giving an engine to you to do this and all that. Of course, Professor Narasimha doesn't go into detail of all this. But this was something that was well known in all other sciences, especially in Indian sciences. In Indian science, the most crucial thing, even mathematical truths in India, many of them were thought of as obtained from repeated observation. But ultimately, you have to have various checks to see that you arrive at general principles from that. And we always knew that there is no sure engine by which this general principle, you can say it's absolutely universally valid for all times and all situations. There are people like Charvakas who said no generalization is possible, so no science is possible. But most science said for all practical purposes, this is a. So this was called the basic problem of Anumana, called Vyapti Graha Upaya. How to arrive at a general principle from observation. So whatever Bacon had said, and later on John Stuart Mill is supposed to have said this positive instances, negative, all this is there, Anvaya method, Vyatireka method, and all that is in old books of Nyaya written in 5th, 6th, 7th, 8th centuries. So this is the basis of science was induction, not deduction. Induction to get general principle, then deduction. Deduction is what Wittgenstein called as tautology. It is all there already in the axioms. Only you have to deduce the conclusion by a suitable method. It is saying nothing new. It contains no more information than in the axioms. So crucial thing about science is to arrive at this general principle. So this Newton's laws were discovered. But there's a huge line to this Newton's law. Bacon wrote this book and Newton's law came. No, not that way. The first thing was to discover that the velocity is constant, not because of a force acting, but because when you apply a force, the body acquires certain thing, which we today call as momentum, etc. They called it as impetus. In India, this was called Vega by Vaisheshika Sutra in 5th century BC. So the body acquires this Vega due to which it moves. But this Vega changes if there is an obstacle, if there is a change, if there is a force on it. So this, what is called the first principle of Galileo, etc., later on the first law of Newton. Every body continues to move in a state of uniform motion in a straight line unless otherwise disturbed by a force, etc. And then quantitative studies showed you that it's the rate of change of velocity that is related to force, especially in falling bodies or friction or inclined plane, everywhere. So like this it leads to, and then the celestial motion. We had entire huge amount of data of celestial motion with complicated geometrical pattern of moving. So finally coming from circular orbit to elliptical orbit and things. All this led to the Newton's laws. It's not just that suddenly some induction principle from that Newton deduced anything. Of course, Newton wrote his great book in that manner. He wrote it in the style of Euclid. There is very few equations in it, little algebra in it. And first two chapters are discussing the laws and how various conclusions are done. Most important conclusions are deriving the central force law and elliptical motion of them and perturbations on them and all that. Then even tides and things like that. And various other smaller phenomena on Earth and in the sky. So astronomy was the major input for the discovery of Newton's and validity of Newton's laws. Then on Earth. So this is the new thing. But the thing is, Newton said that everything that he discovered is universal. So his law of gravitation is universal law of gravitation. His laws of motion are universal laws of motion. So they thought they had unraveled the whole truth of the universe. You have this equation, then you know everything. But you give that equation to anybody and ask him how to do something, he will not know. You have to know then what are the other inputs that are needed in that particular problem. So it's not just an equation, it's a method of going about looking for various things and all that. But the philosophy is put in a particular way as if there is some axiom and deduction in that. Then there is no need for millions of papers published either in classical physics or quantum physics. So everything is a trivial deduction from a set of facts. It's not like that. But anyway, that's the philosophy we are all aware of. So this was a very powerful method that modern West came with it. But this universalization of whatever they discovered was from the Greek. The Greeks said they had discovered these eternal laws by which the planets move. And modern Europe said we have discovered these eternal laws by which all motions occur, all changes occur. And now they finally put it into a metaphysical form that this is how God created the world. So be it Galileo, be it Descartes, be it Newton, be it Hoyle. So everybody said we are discovering the laws by which God has created the world. And therefore they are eternal. And doing all this is a very good philosophical and theological enterprise also, because you are trying to understand the mind of God. Meaning, so it was a metaphysical, theological exploration. Suddenly, the laws of motion became a divine creator commanding the universe to follow a set of laws, like an emperor commands. So, this philosophical idea that science deals with laws of nature is a 15th, 16th, 17th century innovation. It is a metaphysical innovation inspired by both the Greek philosophy and Christianity. But that fact that it was metaphysical, and it sounds very strange that we do some experiment here and then say we have discovered the laws by which universe has been created. It looks sort of somewhat very pedantic in the ordinary sense of the term. But Western civilization was about to conquer the whole of the world and this, and so they are used to this level of hyperbole and this kind of metaphysics. So Professor Narasimha will not go into all this, but this has proved effective in the sense that whichever domain you go, they tell you what to do this, do this, do this. How much effective will be, how much final result is exactly in consonance with what is happening is not always important, but it will give you some handle on what is happening. So they have a method, so you can do that. But they don't want to say that for this situation we will do this. They will not say that at atomic scale we will do this, at the scale of microns we will do this, at the scale of meters we will do this, at the scale of kilometers we will do something else, at the scale of light years we will do something else. Of course they have different subfields, sub-disciplines, and not each one of them is reducible to the other in a trivial or even in a very profound manner, but they are consistent with each other, not derivable from each other. So this is the kind of enterprise that we are doing in modern Western science. But all this is because that we are generalizing principles from observations, and we are making models, we are making theories. So the point Narasimha said that Indians did not infer these models from observation, or they did not pay too much attention, etc., which I am not sure is the correct picture, because if you see the way they developed whole science of Ayurveda, whole science of chemistry, whole science of physics or language, every rule of Panini is a generalization from observation in language. Every sutra, there are 4,000 of them. So this is a sort of, because he had reached a wonderful point by comparing that Europe had a new impetus by looking at observations and inferring axioms rather than thinking of axioms as self-evident.